Yes, good morning, everybody. And today we will give some problems about matrices, about in the linear equation system and maybe determinant. For example, this one, let A and B symmetric matrices, it's okay, and show that A plus B is symmetric, it's okay, and also the next one, show that AB is symmetric if and only if A times B, B times A, it's okay. So we have two matrices, but should be symmetric matrix. We claim that compute the sum A plus B, sum of the two matrix also symmetric. If every here and the two matrix symmetric, and the next one AB is symmetric if and only if AB is equal BA. It's okay. So first of all, let's show that. And our matrix AB is symmetric matrix, is okay. Our aim is to show that AB is symmetric matrix or not. It's okay, that's one. So you know the definition of the symmetric matrix. What's the symmetric matrix? Symmetric matrix should be square, we know and this one. And if A is symmetric, we know that take the transpose of A is equal A. And also B is a symmetric, means transpose of B is B. And we know the transpose, how to get the transpose of any matrix, change the column or row, and then we obtain the transpose. It's okay. Look at this definition, and we can say that A and B square matrix. It's okay. Of course, and the question A plus B is symmetric and means, of course, this one is and gives a matrix and the same and the dimension. Otherwise, this sum undefined. It's okay. So this one is square matrix. This one square matrix. We can mention these matrix A plus B and means and the same and the dimension, row and column dimension, n by n. It's okay. So A plus B is symmetric. How to show that n matrix matrix? Check that, satisfy the definition of the and symmetric matrix, of course. It means A plus B, take the transpose and check that this one gives the A plus B or not. It's okay. So take the left side. It's okay. Start with left side. AB transpose of AB. We know the properties of the transpose matrix. Transpose of the sum is equal sum of the transpose, means A transpose of A plus transpose of B. And also we know when this one, and the substitute here, transpose of A, and transpose of B. So we obtain transpose of A plus B is equal A plus B, and that is this sum, this matrix, result matrix is symmetric matrix. It's okay? Any question about the proof? No question. Okay. And the next one. Next part. AB is symmetric if and only if A times B, B times A. A times B is symmetric if and only if A times B should be B times A. It's okay? That's all. We know that and the multiplication, we know and the matrix multiplication and multiplication is not commutative. It's okay. On matrices means AB is not equal BA for all AB. We know and this one, but our matrices both of them symmetric and the product is symmetric and this product should be this one. And also, if AB is equal BA, and the special matrix is here, because general, and it's not true, it's okay. So, if, and they take the two matrix, if, and the AB is equal BA, and so AB should be symmetric. It's okay? If and only if condition. Let's start one side, and we get the other side. It's okay? And AB, let's assume that AB is symmetric matrix. It's okay. Symmetric matrix. Our aim is to show that AB is equal BA or not. It's okay. So use a different color. It's okay. Sorry. AB symmetric matrix used in the definition of the symmetric matrix. What does it mean? And the transpose of this matrix gives itself this one. It's okay. This one. So, and also we know the transpose and the properties of the transpose. And we know that under this one, use this property. Which property? Use different color. It will be better. And the but use the different notation. In general, CD, transpose of CD, is equal transpose of T times transpose of C. Because we know that and the multiplication is not commutative. If multiplication is commutative, of course, we can write under this one, but not commutative, we know that. It's okay? So, order it is important. It's okay, be careful, this one. And use this property here. It's okay? So, and transpose of AB is equal transpose of B transpose of A. It's okay. And also we know that an assumption and the AB symmetric matrix. It's okay. So and we have under this one transpose of A is A, transpose of B is B. And they use this substitution B times A. It's okay. So we get, and this one is B times A is equal A times B. It's okay. That is AB is equal BA. It's okay. And but this one is this side. This side. And take that AB is symmetric. Our aim is to show that A times B, B times M. And the next one, you have to and prove and this direction. What does it mean? Because if and only if condition, and they assume that AB is equal BA. It's okay. Our aim here show that AB matrix AB and symmetric or not means that is transpose of AB. Sorry. Symmetric means you have to check that transpose of A is equal AB or not. It's okay? This one. So Take this equality and take the transpose of both sides. So, and this one is okay. So, and what's this one? And use this property, transpose, property of transpose, and transpose of B, transpose of A. And also this one, transpose of B is B because B is a symmetric, and the transpose of A. And no, sorry, but our aim, sorry, not this side. Sorry. Our aim is to show that this one. So take this one, it will be better. Yes, our aim is to show that this one. So take the transpose of AB. So use the definition of the transpose, properties of the transpose, this one, CD, transpose of CD is equal transpose of D, transpose of C, and this one gives transpose of B, transpose of A. And also we know that B is a symmetric matrix, so symmetric, and A is symmetric matrix, so transpose of B is B, transpose of A is A. It's okay? And also look at the assumption, AB is equal BA. So this one is equal AB. So we are done. It's okay? Transpose of AB is equal this one. And what does it mean, this one? Means AB is symmetric matrix, is a symmetric matrix. It's okay? Any question? And here we use only and the property of transpose and also definition of the symmetric matrix. Is okay? Okay, no question. Okay, let's come back. First of all, and let's look at this one. Show that transpose of C of A is equal C of not transpose. Sorry, and this one is trace. Trace of and the C times A is equal C times transpose of trace of A, and also and the next one B. Trace of the sum is equal sum of the traces, and C transpose of the product is equal transpose of the B times A, and the order it's important here. Is okay? Trace. What is the trace? And trace, and this one is second problem. Traces, and they take the n by n matrix. It's okay because then the trace is valid only and is defined only n by n square matrices. It's okay, square matrices. So, and the trace means look at the main diagonal entry and sum of the main diagonal entry. It's okay. Trace of A is equal A sub 1 plus 2 plus A sub n. The sum of all entry on the main diagonal. It's okay, this one. So, and the first one, our aim is to show that C, any scalar, any real number, for example, and trace of C times A is equal C times the first one. We claim that trace of A. It's okay. Let's prove this one. A is a square matrix, And look at this one. What's the trace of A is this one. But if A is, for example, A is denoted by an IJ entry, it's okay, and by N matrix, it's okay. So what's the, and take the C is real number, C times A. C times A is a matrix, we know, and this C is a scalar. Using the scalar multiplication here, we know the definition of this multiplication means, and what does it mean, this one? Multiply all entry by this scalar. It's okay. C times this one means multiply by all entries by C. It's okay. C times this one, C, this one, C times this one. So, and let's use this and the notation, and this one means all entry, multiply all entry by C, and means IJ entry should be C IJ entry. It's okay, and by N, this matrix. So, and our aim is to show that this one is equal right side. It's okay. So start with the and the left side, trace of C times A. So what's the trace? And look at this definition. All and the sum of all entries on the main diagonal. So, and this one is equal sum C A I, and the I is from 1 to N. It's okay, this one. So, and this one means we know that C is a scalar, and every term and it contains and the C and the factor common, and then C, and we can write, and this one is C times summation A sub I is 1 to N. And so what's this one? Sum of all entry on the main diagonal of A. So this one is C times trace of A. It's okay, this one. Or use then this one, trace of CA, and not use the sigma notation, and write all of them, and means, and so C A sub 1 1 plus C A sub 2 2 plus the last entry on the main diagonal C A sub N N, and rewrite this one C times A sub 1 1 plus 2 2 and A sub N N. So C times, what's this one? This one is trace of, and this one is equal to this one, of course. This one is the sum of all entry on the main diagonal of A, so this one is trace of A. It's okay. But I think it will be appropriate, of course, use this notation, sigma. It's okay. Yes, and the second one, and this one, it's okay. Show that trace of A plus B is equal trace of A plus trace of B. It's okay, this one. Let's prove. And A is of course n by n should be, because and this sum is defined, not undefined, and also we can mention the trace, so means, and the result matrix should be square. So, and A and B should be square, and also have the same and the row and column dimension n by n, for example, and the B is n by n matrix. It's okay. So, and what's the addition of two matrix? We know, and this one. And how to get and so we know that this one is n by n, this one is n by n, so our matrix should be n by n. So what can you say about the entries? Entries and the correspond is the sum of the corresponding entries, so means Aij plus Bij. It's okay. This one. All entry, the sum of the corresponding entries. It's okay. So this one. So what is the trace of, yes, that's right, trace of A plus B. It's okay. Entry here, this one is, and ij entry, and means, and this entry is on and ith row and the jth column and column J, and so, and look at the trace of any matrix and look at the main diagonal entries, sum of the all main diagonal entries. So this one, trace of A plus B is, yes, A sub I plus B sub I, A is from 1 to N, this one. So, and we know the sigma notation property, and we can write under this one, A is 1, separate into the parts, and this 1 plus this one. So, and what's the first? And the first one is the sum of all entry on the main diagonal of A. So this one gives trace of A. So this one gives trace of, the next one, trace of B, because sum of the all entry on the main diagonal of matrix B. Yes, we got the result. It's okay? This one. So the next one, show that this one. Trace of AB is equal trace of BA. And here, we know that multiplication is not commutative. If multiplication is commutative and means AB is BA, so it is easy to see that and take this one right here. So we obtain this one. But this one is not true. It's okay, not true. AB is not equal BA in general, because, and we claim that, and this equality and valid for all AB matrices. It's okay, not special matrices. And so we know, and also we know that, and the multiplication is not commutative. So this one is, it is not easy to see that this one is true. So let's look at the left side. It's okay. So A is, and here A is this matrix, and B is this one, Bij. And also, what can you say about the dimension of AB? A, for example, A is n by n matrix. It's okay. We know that this one is squared or not, n by n. It's okay. But here, and we can mention the trace of this product. So this product is defined. Defined and means, and this one should be is equal m by k, for example. It's okay, m by k. But, and also, and the question, use a different color. We can mention the trace of these products. So means, and this matrix should be square matrix. So A times B should be square. And so this one should be this one. It's okay. So we obtain under this one. And also, and the trace of BA is okay. Trace of BA. And the M is M by N. And this one is equal this one, and means this one is defined, this one is defined, not undefined. So this one should be square. So, and B times A, this one is M by K, it's okay, K. And A is N by M. But this product is, yes, the same So, sorry, this one is equal this one, K is N. It's okay. So, and we can see that, and this one is equal, and the dimension the same. It's okay. So, and square matrices. It's okay. This one is square matrices, AB square matrix, and also same dimension. So, and for example, take the, and this one is usual one, yes, n by n matrix. It's okay. What is the AB? AB is a matrix. It's okay. N by n matrix. For example, this one is gives a matrix. For example, is noted by C. So let's define the C. What's the C? C entry Cij. It's okay. So n by n matrix. N by n matrix. So, and here, what's the Cij? We know the matrix multiplication, so Cij should be, yes, we know, and this one, and we know the multiplication of product of the two matrices, and the result matrix entries Cij will be, yes, look at the, and this one, AB is, yes, A, B, and so this one should be, yes, A is from 1 to n. For example, K is 1 to n. A sub K, Ki. I sub K, Ki. This one is okay? Sorry, not this one. This one. Because, and not the trace. Take trace, okay? Sorry. This one. Cij should be this one. And how to get Cij? Choose row I. It's okay. And choose the column J of B. It's okay. This one is A. This one is the matrix B. This one is column J, row I. So, and product of the all and the corresponding entries, and also the sum of these products. It's okay. This one. So let's come back here. Our aim is to compute the trace. So, and trace of AB is equal trace of C. So it is equal, what's the trace? We know the definition of the trace, the sum of all entries of the main diagonal entries. So, and the Cij all entries, so means Cii, and such that, yes, such that I is from 1 to n. This one is trace of C. Yes. So what's the Cii? Cij, this one is okay. And this one is here, the spatial and the element. I is equal J. It's okay. Sorry, this one is should be J. It's okay. J. Sorry, wait, please. Yes, let's come back. Sorry. Yes, and the R Cij, take the row I, take the J column, because and the second index is J. So, and this one is I sub 1, this one is B 1J. It's okay. So, and IK J. It's okay. This one is okay. So right here, special case, and take I is J entries. It's okay. So, and sum sum I is from to n. Substitute here j I is okay here, and right here sum, yes, k is 1 to n I sub k b k I, because I is j here. It's okay. Any question about this part? Okay. So, and this one is, this sum is, yes, is equal, k is 1 to n, sum I is 1 to n, and also we know that, and this one is a real number. Use a different color, maybe it will be better. It's okay. This one is real number because entries and our matrices and entries coming from and the real numbers here. So this one is real numbers. So we know that multiplication, take the 2 and the, for example, CD real numbers, always D times C for all real numbers. It's okay, this one. So interchange the and the order. So we obtain BKI and I sub K and this one. It's okay, same. So, but our aim is to show that trace of AB is equal trace of BA. Now, let's compute B times A. B times A is any matrix D and is denoted by, for example, Dij and by n matrix. It's okay. So, let's compute the trace of BA. So we know that sum of the main diagonal entries DII, I is from or K, use the different color, different index, because our aim is to get then this one. It's okay. So use the, for example, DKK, K is 1 to n. It's okay. All entry on the main diagonals, sum of the main diagonal entries. So, and substitute, and so we know that here Dij is equal, what's this one? Use the product rule. Sorry. But right here, I is equal J and the special and the entries, right? Sum K is 1 to n, right? Yes, sum, but order it is important. B times A is okay. Here, B times A is, for example, A is 1 to n, B I K. This one is okay. So we obtain the same result. It's okay, is equal. So trace of AB is equal trace of BA. It's okay. Any question? No question, okay. Let's come back. And here, find the reduced row echelon form of the given matrix. This one and this one. It's okay. So let's solve the one of them. For example, this one. It's okay. And here, yes, Using the elementary row operation is okay, of course, but not use the column operation. It's okay because this one is a matrix, not determinant. Be careful. It's okay. So, and our aim reduce row echelon form. To reduce row echelon form, yes. Start it and this one is okay. Is 1, yes. And our aim is to get 1 0 0 column. So, and how to get 0 here, 0, and they take the leading one, multiply by -2, add to the second row. And our aim is to get in this position 0, so take the leading one, multiply -3. It's okay, apply to this operation, yes. And the first one, the same, 1 2 3, this one, it's okay. So apply the this one, this operation. Multiply, take the first row, multiply by -2. -2 plus 2, 0. -2, 2, -4, -1, -5. It's okay. -6 plus 1, -5. Yes. And now let's apply the next one. Multiply by -3, add to the last row. -3, 3, 0. -3 plus 2, -3 times 2, -6 plus 0, -6, yes. -3 times 3, -9, -1, -10, yes. It's okay. We obtain the second and the matrix. It's okay. So the next one, to get leading one of the second row, and it is easy to get the here 1. So multiply by 1 over -5. It's okay. So we get, yes, we get 0 1 1. Yes. And the next one, but not apply to this one, and the -6 and the -10 here. It's okay. So the next one, to get 0 here, this position is okay, here 0. So, and take this one, it's okay, multiply by and 6 and add, it's okay, to the last row. And then we obtain 1 2 3, same, and apply to this operation, 0 0, and this one -4, this one. And then we get 1 here. How to get? Multiply -1 over 4, so we get 1 2 3 0 1 1 0 0 1. So, and this one is row echelon form, reduced row echelon form. And to get here 0 0 1, how to get? And multiply by -1, multiply by -3, and then we get 1 2 0 0 1 0 0 0 1. Yes, one more operation, multiply by -2. So we obtain this matrix, identity matrix. It's okay. Reduced row echelon form is this one. So, and this one is homework, and also we have an answer here. Let's skip. Now, yes. Solve the following and the linear system. It's okay, linear system. But here, and the coefficient 0 coefficients right here, 0x 4, but this one is, and delete, it's okay. This one, 0, 0 because 0. It's okay, this one, this one. And also this one is 0. Don't write in this one, this term, it's okay. So, and they find, and this one is homework, it's okay, homework. And let's solve and this one. It's okay. This one. So how to solve any linear system? We have some in the Gauss-Jordan reduction or Gauss elimination, or and X is A inverse B, or and the Kramer. But look at this one, and the coefficient matrix not square, And so the dimension of a coefficient matrix is 3 by 4, not square. So, and the Kramer, our matrix should be square, and also use the inverse matrix, but this one is not square. So, and this one is not valid, this method. So, you have to use and the Gauss-Jordan or Gauss elimination. It's okay. So, because our coefficient matrix is not square, because we have 3 equation but 4 unknown. It's okay? 3 by 4 equation. So, what can you say about the solution of the system? We know that, and let's write here our system, this one, 2x1 plus x2, no, not this one, sorry. 2x1, 2x cubed minus 4x4 is this one. The second equation, x2 plus 2x3 minus x4 is 3. The last equation, 2x2 plus 5x3 minus 4x4 is 9. It's okay? Solve under this system. So, and what can you say about the solution of this system? It's okay? Now, and we know that any system, linear equation system, AX is B, linear system, we have 3 cases. Maybe no solution, maybe unique solution, has unique solution, maybe sorry, no solution, maybe unique solution, maybe infinitely many solution. Infinitely many solution. It's okay. So here, what can you say about our system? Yes, any idea? This system has no solution or unique solution or infinitely many solution? Yes. Any idea about this system? It is possible to get the unique solution here. Unique solution and means no free variable. No free variable. It's okay. And so, and here the number of equation 3, but the number of variable 4. Not enough to get the 4 and the leading one. So it is not possible to get the unique solution here. So maybe and 3, 4, and if our matrix has no 0 row, but then the one of them, and so at least one free variable here. So infinitely many solution, but maybe we get contradiction some step, maybe no solution case we obtain. It's okay, but unique solution it is not possible for this system. It's okay. What's the reason? Because the leading one and every equation has one leading one. So we obtain the number of leading one is 3, but and the unknown number, the number of unknown 4. So and at least one free variable. It's okay. If we get 0 row, so we have 2 free variable maybe. Maybe we get contradiction, so this system has no solution. It's okay? So, and let's solve this one. Let's see the answer. It's okay? So, first of all, you have to write the augmented matrix, and augmented matrix, write the coefficient matrix. Coefficient of x1, 2, 0, 0. Coefficient x2 0, 1, 2. Coefficient of x3, 2, 2, 5. Coefficient of x4, -4, -1, -4. And right side, this one is left side coefficient matrix, right side, right, minus L, 3, 9. This one is called augmented matrix. It's okay. Write the augmented matrix, and our aim is to get the reduced row echelon form. It's okay. Gauss-Jordan reduction method, let's use and this method. So to get 1 here, multiply 1 over 2 is, yes, 1, 0, 1, minus 2, minus 6. 0, 1, 2, minus 1, 3, 0, 2, 5, minus 4, 9. So the next one, to catch the leading one of the second row, yes, we have. So the next step to get 0 here in this position. It's okay. So how to get the 0 in this position? So take the leading one and multiply by -2. So use and this operation. First one the same. 0, 1, 2, minus 1, 3, and apply the operation. Take the second row, multiply by -2, add to the last row. 0, -2, 0, 0. -2 plus 2, 0. -2, -4, 5, 1. -2 plus 2, this one, -2. It's okay. And also this one, -6 and 3. It's okay. Any question here? I hope no question. Yes. So to get 1 here, but we have 1 here. It's okay. Leading one of the last row. So this one is in reduced row echelon form. But our aim is to get reduced row echelon form. Now, take the last leading one. Our aim is to get 0, 0 here. So how to get? Take this one, multiply by -2, add to the second row, and the next one, take the last row, multiply by -1, add to the first row, is row equivalent. The last one the same, 0, 0, 1, -2, 3. Yes, apply the operation please. -2, 0, 0. 0 times -2, 0, 1, 1. -2 plus 2, 0. -2 plus 4, -3. -6, -3. Sorry, this one is -2 plus 4, -1. This one should be plus. This one should be plus, sorry. And then next operation, this one, multiply by -1, add to the first one. 0, 1, 1. 0 times -1, 0, 0. And -1 plus 1, 0. Plus 2, this one, 0. It's okay. So -3, -6, -9. Yes. So what's the next step? Yes, what's the next step? To get leading one, but enough. And this one is, yes, unique non-zero entry is leading one. Unique non-zero entry leading one. Unique non-zero entry leading one. So this one is reduced row echelon form. So this one is in reduced row echelon form. Write the corresponding equation. This one is column x1, x2, x3, x4. So first row gives x1 is -9, and the second row, that's right here. First row gives x1 plus 0, 0, -9. It's okay. And the second row gives this equation. Which one? X2 plus 3x4 is equal -3. And the last row gives the last equation. X3 minus 2x4 is 3. It's okay? So So, and last equation. So we obtain this system and solve this system. How to solve this system? Yes, and solve for unknown. Which unknown? It's okay. First one and the first one x1. This one. So we have two unknown here, x2, x4. Solve for one of them. Which one? But be careful, and the critical point here, look at the leading one. Leading one, this one. So solve for x2 means, it's okay? x2 is minus 3, x4 minus 3. And we have two unknown here, x3, x4. Which one? And the solve for which one? One of them. This leading one is associated with the x3, so solve for x3 means x3 is 2x4 plus 3. It's okay, this one. So, and here, look at the last matrix, and we have three leading one, and so means x1, x2, x3 basic variables. So x4, look at the x4, no leading one for x4, and means x4 is free variable. So our solution depends on free variable. It's okay, this variable. Look at this one. Yes, depends on x4. x4 free variable. So x4 free variable, and means take the any real number x4. x4 is our any real number. Then our solution depends on r. It's okay. x1 is minus 9, x2 is minus 3r minus 3, and x3 is 2r plus 3, x4 is r any real number. So we get, and if we get the free variable, so we get infinitely. So our system it has infinitely many solutions. It's okay. So, and the question, of course, every and the tuple or the tuple is a solution or not? No, because what's the reason? Look at this one. Write the type of the solution. It's okay. So write the solution set. Solution set is denoted by S. Write the x1, x2, x3, x4. So this one is, yes, minus 9. x2 is minus 3r minus 3, 2r plus 3r. It's okay. And the rewrite under this one, look at the coefficient of r. Coefficient of r, sorry, this one is no r, 0. This one minus 3, 3, 1 is this one. It's okay. So, and rewrite this one, coefficient of r, 0, minus 3, 2, 1 times r, but not enough because constant term, minus 9. And this one gives minus 3 plus 3, 0. R plus. It's okay, such that R any real number. For example, take the R is 0 here, we get, and this one is the solution. x1 is minus 9, x2 is minus 3, x3 is 3, x4 is 0. It's okay. So take R is 1, and we get other solutions. So we get infinitely many solutions. It's okay. Any question? Any question about the solution? But be careful, it's okay. So look at the leading one, solve for the and the corresponding unknown. It's okay. No leading one means, and these and the variable is the free variable. So free variable and means infinitely many solutions. It's okay. Any question? No question. Okay. Let's stop here and let's have a break. It's okay. And the 10